I'm Gemma, and this is our work called Multitwine, multi-object compositing with text and layout control, which was done in collaboration between Decade at the University of Surrey and Adobe. Most state-of-the-art compositing models only accept one object at a time, meaning that if the user wants to composite multiple ones, it needs to be done in a sequential manner. However, as you can see in this example, adding the objects in one order or in the other sometimes leads to very unnatural and unwanted results. However, if we composite both of them simultaneously, we can repose them according to their interaction, harmonize them simultaneously, allowing visual coherence, and if necessary, automatically generate any prop or additional element. Like in this case here, where the model automatically generates the TV import into a cap. Our model accepts several inputs, including multiple object images, a text prompt with grounding information, a background image, and a layout with a bounding box specifying the location of each object. This way, the user has multiple tools they can use for communicating the exact expected outcome. So, by changing even one input, like the object's layout, they can obtain different compositions with very fine-grained control. The pipeline proposed for this task is based on the pre-trained stable diffusion. The input to the UNet is the encoded concatenation of the noisy input, the masked background image, and a mask specifying the position for each object, as well as the area to paint. Additionally, we accept as input the images for two different objects and a text prompt with grounding information for both of them. We train with two images, but we actually find that by doing that, the model learns how to deal with interactions and can be used to compositing 3, 4, or even more objects at the same time. Then we encode each object image via Dino and an adapter module, and the text caption using Clip. After, we built a multimodal embedding by concatenating the encoded visual information of each object after their corresponding text token, obtaining a big embedding that combines visual and textual information, which is then fed to the UNet via cross-attention. This way of combining multimodal information leads to two main challenges. First, the balance of textual and visual information, and second, the prevention of identity mixing for the different composited objects. For ensuring a good balance between textual and visual information, allowing objects to repose and follow the text description without losing their identity traits, we added customization as an auxiliary task. Therefore, during training, we only provided the background image 50% of the time, and the other 50%, the model was free to complete the generation with any natural background. This way, in those occasions, the model didn't need to focus on the compositing subtasks of harmonizing and blending boundaries, and could focus solely on combining both input modalities. For the second challenge, we focused on the object's attention maps and encouraged them to match their corresponding segmentation maps by introducing some training losses and also adding an attention masking step at inference time. This model required some paired training data, including ground truth images with paired objects, masks, and grounded descriptive text. But we needed to ensure some criteria, including a diverse range of objects and relationships, different kinds of text prompts, images of different views for each object, high-quality images, and a large size of dataset. Since those are a lot of constraints to meet, we had to rely on different sources and collection strategies, including video data, in the wild images with paired captions, and a small manually collected dataset. As an example, from a single image, all the necessary training data was obtained via the combination of a subject selection tool, a semantic segmentator, and a vision language model, VIP-Lava. For more details about this and the other data collection pipelines, please refer to the main paper and supplementary material. Our model's ability to perform simultaneous multi-object compositing was evaluated by comparing to state-of-the-art compositing models in a sequential manner, showing its advantages both in terms of quantitative metrics and user studies. Additionally, we also compared to several multi-object customization models, obtaining a comparable performance, hence proving the versatility of our model to adapt to different tasks. For more details about our model, data collection pipeline, and the different experiments, please refer to our paper or come visit our poster on Friday the 13th. Thank you for your attention.